I'm going to be following up on the presentations you saw from Christine, and now I'm taking it to the next step, which is talking about bringing climate change down to the local scale, which is a lot of my research and what I do work on. So as I go along, there's this weird thing sticking out here that I can maybe that's for short presenters. There's like a platform that comes out of the bottom that you can stand on. Never seen that before. It's a good idea though. Okay, I've pushed it in, so I'll turn on it. Okay, as I go along, I'm going to stop and ask for questions or clarifications, and don't be hesitant. So if something I said did not make sense, or if you have a question about it, or if you want to kind of go into it a little deeper, make a note, and I'm going to be stopping periodically and asking for questions. Because the whole point here is to give you practical information that's useful, not to just bombard you with a bunch of stuff. So I want you to go away actually understanding what I'm saying, which I know is not always the case with people talk. All right. I'm going to start with the basics, but I'm going to start with a bit of a different perspective, and that is the question of why do we even need high-resolution climate projections? We have really good historical records going back decades and even centuries in some places. If you combine paleo data into it, you can go back millennia, and you can look at patterns of droughts in California going back 5,000 years, for example. Or we can look at heavy rainfall events, or we can look at ENSO frequency or intensity. All of this information goes into planning. It goes into planning in terms of the 100-year or the 500-year flood zone. It goes into planning in terms of what types of crops we can grow where, what our energy requirements are when we build a house, how big an air conditioner we have, how much we insulate the attic. It goes into all kinds of planning that we don't think about. And all of that planning is built on an assumption that almost never is consciously voiced. And that is the assumption that we can have ups and downs. So we can have heat and cold, we can have wet and we can have dry. But our human civilization, our human society is built on the assumption that climate is stable. Why? Because over the course of human civilization, over the course of becoming an agricultural society, building buildings and roads and infrastructure, allocating land so that people own it now as opposed to just picking up and moving when you wanted new land. Over the course of that happening, climate has been quite stable. The warming after the last ice age peaked when? Anybody know the answer? How many thousands of years ago did warming peak after the last ice age? And Christine is not allowed to get Spanish. Any guesses? 125,000 years ago. That is too high. Let's get a lower guess. Good guess though. That was when the Ice Age peaked.
Like 10?
Yes. 10. Very closer. I'm sorry I don't have a water gun to get out. Any other guess? We're getting closer. 12? 12. Wrong direction. 8. We have a winner. Warming peaked 8. But see, now you remember it more because we went around a few times. I actually used to think it was 6, but it turns out it was 8. So warming peaked after the last ice age about 8,000 years ago. And ever since then, our Earth's temperature was on a very, very gradual, slow cooling slide into next ice age. But two things happened. First of all, in the last 8,000 years, people discovered agriculture. So we cut down a ton of trees. We planted a lot of crops. We started to grow large herds of ruminants and other animals that produce a ton of methane, which is an enormous heat-trapping gas. And we began to stabilize climate. Isn't that interesting? So it would be a lot cooler now if it weren't for the development of agriculture. In other words, we took that cooling trend, that slow cooling trend, and we moderated it to the point where it was incredibly stable. So not just into our building codes or our engineering standards, but into the history of the human civilization is built the assumption that you can have the little ice age, you can have the medieval warm period, you can have heat, you can have cold, you can have wet and dry, but it all averages out in the end. Why do we assume that? It's because it was true. It was true until when? Until the Industrial Revolution. That was when, instead of producing a small amount of carbon dioxide and methane from agriculture, we started to produce a huge amount from burning fossil fuels. And that is when the wheels started to fall off the bus. Today, climate is no longer stable. Today, climate is changing very rapidly. And if you want a very visual picture, actually, of what I'm talking about, because it's helpful to see a visual picture, isn't it? For a visual picture, there's a great paper by Sean Marcotte et al. And I'm going to find you the picture from it. If you just Google Marcotte temperature and look for your images here. Here is the image. This is the image. Look at this. Come on, Texas Tech Wireless. Seriously? Okay, we'll just look at it here. There, you can see that, right? Yeah. Okay. So there you have it. You have the warming peaking. Depending on when you put the dot, it is sometime between 8,000 to 6,000 years ago. And then you have the slide. And this slide looks a lot more dramatic than it was because it's so many thousands of years squished into just a few years. And then what do we have at the end? We have something crazy. See that red line? That's the instrumental temperature record using thermometers over the last 150 years. We're warming about right now we're warming about 10 times faster than the warming after the last ice age. And if we continue on our current pathway, depending on fossil fuels, we'll be warming about 50 times faster than after the last ice age. So this assumption on which our society is built is no longer valid anymore. And in fact, it isn't just the fact that climate is changing extremely rapidly over human timescales. That's really the issue, is human timescales, right? Because when we build infrastructure, it's built for what, 50, 80, 100 years. If things were changing rapidly over 1,000 years or 10,000 years, it wouldn't be a big deal, but it's changing rapidly over decades. It isn't just the fact that the mean is changing. What's also happening, and we notice this especially here in Texas, is that we have this pattern of variability. If you live in some places, you know, the pattern of variability looks like this. If you live in Texas, the pattern of variability looks like this. And what's happening is, as climate changes, this pattern of variability, which is already very large, is being stretched. So we have experienced it here in Lubbock simultaneously in the past 2 decades, or the past decade alone, sorry, the last 10 years, we have experienced the coldest winter on record and the warmest summer on record. We have experienced the greatest drought on record and the longest dry period on record, and we have also experienced the wettest years on record, and that has happened all in the last 10 years. So the variability changing is also a huge concern, and that's why we need climate projections, because if this assumption were valid, we could just look backwards. All we would need is really good observational records and some really good paleo data, and we'd be done. You'd have a talk by Christine, and then you'd have a talk by somebody who does instrumental data, maybe satellite data, and then that's it. But instead you get Keith, and then you get me, and the reason why you get me and Keith is because of this. So what is our goal? Our goal, when we're looking at producing high-resolution climate projections, is to give people information. We want this to be useful information that we can use to assess the impacts of climate variability and change. We want to look at human and natural systems both, especially those whose processes operate at a finer spatial and sometimes temporal scale than the global climate models. That's our goal here. In other words, we want to go from looking at a forest of trees like you get from the global climate model to looking at a single tree, say, a state, a region, even a city. Now I know Keith talked a little bit about this, but I'm going to begin here again, both because you had a break and also because sometimes we have to hear things multiple times to retain it. When we talk about future projections, they are subject to 5 main uncertainties. One uncertainty is the uncertainty of scale. And that's what we're going to talk about the rest of the time, is the issue of scale, especially spatial scale. But the first 4 are common to any type of future projection. First of all, they're uncertain because we have natural variability, which is chaotic. And chaotic means simply that it depends critically on initial conditions. Initial conditions that are often not resolved by observations. So natural variability is chaotic. Climate sensitivity is unknown. You've probably heard the phrase that we're conducting an experiment with our planet of a magnitude that's never been conducted before. Nobody has ever put this much carbon dioxide and methane into the atmosphere when the planet was already this warm. It's never happened. So that's why climate sensitivity is unknown. Our climate models are imperfect. And in fact, those of us who work with climate models know even more than anybody else how imperfect they are, because whenever I work with a climate model, half the time what I'm doing is trying to poke holes in it and find where it's wrong. And then there's perhaps the biggest uncertainty of all, and that is the fact that future scenarios are driven by human activities. If we go backwards here to here, why is climate no longer stable? There's one big reason for that. That reason is people. Exactly. And so people are the #1 uncertainty. Skip slides easier. There we go. People are the #1 uncertainty in future projections the farther out that we go. So in brief, how do we deal with each of these sources of uncertainty when we're going into the future? Well, the first thing we can do is simply understand that they're different. It's not some big gray mass of uncertainty. The uncertainty in future projections comes from very specific reasons, and understanding what those reasons are is step #1. Step #2, for each one of those reasons, there's specific things we can do. What's the thing that we can do with natural variability? With natural variability, we can make sure it's natural. We can make sure that we look at future climate over appropriate time scales. To illustrate that, I'm sharing with you this plot, a plot that I made when I was working with the state of Delaware. This is looking at annual maximum temperature, so annual daytime temperature, from 1960 to 2010. The black line is the observations, and all of the colored lines are different models. Now, when you look at this naively, you might say, oh my goodness, those models are all wrong, aren't they? Because none of them matches the black line. Why do these models not match the black line? Reason #1, natural variability. Each climate model, as Keith probably explained, is like a different planet. It has the same external forcing, but it has its own unique pattern of internal variability. So you might say, well, why are these models useful? Well, if you drew a trend line through this 50 years of data and simulations, those trend lines would be almost identical. Why? Because these are climate models, they're not weather models. Weather is what's happening here and now from day to day, week to week, even year to year. Climate is the long-term average of weather over at least 20 to 30 years. So we address climate variability by looking over climate timescales. And in fact, climate timescales were defined for a reason. They were defined for a reason because natural variability, including cycles like El Nino, occur over timescales shorter than 20 to 30 years mostly. Now, there are a couple of longer-term cycles, but the biggest ones that impact local scale conditions happen over shorter periods of time. So when we're using climate models, does a climate model give you a value for July 18, 2064? It does, actually. It does give you that value. You can pull it out. Do you trust that value? No, absolutely not. Why? Because it's not a weather model, it's a climate model. Would you trust a value that gives you, say the average summer temperature for 2040 to 2075? Yeah, that's a reasonable amount of time. Maybe even for 2030 to 2050, but not for a specific year or a specific day. The next two sources of uncertainty are scientific. They have to do with our scientific limitations. #1, we don't know exactly how sensitive the planet is to the experiment that we're conducting with it. And #2, our models are not perfect. So let's talk about the sensitivity issue first. Climate sensitivity is the result of feedbacks, or as Susan would call them, I don't know if she mentioned this yesterday, but a lot of our words are not well chosen because if I give you positive feedback on, if I give you positive feedback on your paper, what do you think that means? Did you talk about this yesterday?
Yeah.
Okay, good. It means you did great, right? Whereas if we have positive feedback in the climate system, what does that mean? It means runaway global warming. It's a bad thing. So it's really better to talk about vicious cycles than positive feedback, and that's a tension that we always have, along with many other words, which I'm sure Susan brought up. We know, for a given amount of carbon dioxide, we know how much extra heat that carbon dioxide traps. That is very clear. You can measure it in the lab. What we don't know is how that extra heat affects the rest of the Earth system. Here, for example, is and I'm sorry to say this, it is literally a simple diagram of the feedbacks in the climate system. In the climate models, we have all the feedbacks that we've put into them. And that leads to different amounts of sensitivity. So again, taking some examples from Delaware, if we look this time at projected change in annual average temperature for the state of Delaware from 1950 to 2100, we can use models that have feedbacks that produce a lower climate sensitivity, the green lines. We can then use models that have a medium range climate sensitivity, the warmer colors. And then we can add on some models that have a higher climate sensitivity. And what does this give us? It gives us a range. What is this range? This range is a range in the sensitivity of the models. What types of feedbacks are we talking about? We're talking about feedbacks with water vapor, with clouds, with ocean circulation, with melting ice, and we're talking about some feedbacks that are not in most climate models. This article just came out on June 1st. Arctic methane emissions greater than previous estimates. But honestly, I've seen an article with this title about every 3 months for the last 3 years. What does that mean? It means every single time it's getting greater and greater and greater. What's happening in the Arctic? Permafrost is thawing, and it's releasing trapped carbon and methane from the permafrost. The atmosphere doesn't care if that carbon and methane is human-caused from fossil fuels or if it's coming from the permafrost. It has the same warming effect. We also know there's a huge amount of methane trapped under the ocean in the continental shelves, which is leaking out as the ocean warms. That methane has not yet been measured to reach the surface. It's being absorbed by the water column so far. But it is certainly possible that in a rapidly warming world, those hydrates, as they're called, would destabilize so quickly, and there would be so much of that gas released that some of it could make it up to the atmosphere. It hasn't happened yet again, but it could. Most climate models do not include methane feedbacks from thawing permafrost, and no climate model includes methane from hydrates. What's the result of that? Well, the result of that was investigated by a paper by Naomi Oreskes and colleagues. You're probably familiar with Naomi. She wrote Merchants of Doubt. Really good movie if you haven't seen it, or you can read the book. This is a paper that Naomi and her colleagues published. And she addressed an important topic. She said, skeptics of the reality and significance of anthropogenic climate change have frequently accused climate scientists of being alarmists. You heard that? In fact, I actually got this the other year, I think it was 2 years ago, from my program director here at Texas Tech. Great man, totally supportive of my work. But he pulled me aside one day and he said, Katharine, you know, I've been thinking, if you could just tell your colleagues not to be so alarmist. Because they cry wolf so many times, it just makes people skeptical when something, really happens. And so I said to him, well, luckily I have a paper for you because they have examined this claim. Are scientists typically alarmist? So what they did was, and this was really smart, they looked at 20 years worth of climate projections from 1990 to 2010 to see if they're systematically over or underestimating future change. Because if climate scientists are being alarmist, we'd be systematically overestimating the rate of change, right? Here's what they found. They found, from reviewing hundreds, and I think perhaps even thousands of peer-reviewed papers, that scientists have in fact been conservative in their projections of the impacts of climate change. So conservative that we're biased towards being cautious, where we define caution as erring on the side of less rather than more alarming predictions. It was so systematic, they coined a syndrome that climate scientists are subject to, ESLD, erring on the side of least wrong. So when you see climate projections coming out of our models, we have to put an asterisk beside them, and that's my asterisk. Climate sensitivity is unknown, and the one thing we do know for sure is that climate models are not including some of the feedbacks that would lead to even greater warming. And that is a serious issue, and that is definitely probably one of the issues that keeps me up at night. Issue number 3, models aren't perfect. One of the reasons models aren't perfect is because of their resolution. You can see they're getting a lot better over time, but they still have a long way to go. Imagine how hard it is to model something like precipitation What scale does precipitation occur at? Millimeters or even less. Imagine modeling a physical process like precipitation over 100-mile grids. That is what they call a wicked problem. And it is going to be a very long time, if ever, before we see millimeter scale climate models. Yeah. Now, they do have meter scale climate models for some urban applications, so, it's not that, necessarily that far off, but global models at a millimeter, I don't know if we'll ever have them. We might not even need them. There's also not just an issue of spatial resolution, there's an issue of including all of the factors that matter. When they first started running climate models with future projections on a regular basis back in the 1970s, there was an atmosphere, there was the sun, there was rain without clouds, a miracle, and there was no ocean. They added the ocean, they added ice, they added land surface. It wasn't until the 90s that there was actually GCM's atmosphere ocean general circulation models with circulation of the ocean. Now there's chemistry, now there's Earth system models that have a carbon cycle in them. But these are all pretty important parts of the climate system. I mean, how can you model climate without a carbon cycle? Well, we've been doing it for a couple of decades and we're just starting not to do it now. So there is a lot of improvements that are coming in the models. A lot of the work I do is climate model evaluation. Here's one example from a few years ago that we did, looking at ENSO. This is simply the observed pattern of sea surface temperature during winter or during an ENSO event. And then over here on the right-hand side, you see a bunch of CMIP3 models with their best ENSO pattern. What do we see? Well, they all get an ENSO, that's good. That's actually pretty cool, right? Because you don't put El Nino into a climate model. What you put into a climate model, you put all the physics. And somehow, when you put in all of the physics of nonlinear fluid dynamics and radiative transfer, and when you apply that to a fluid on a rotating globe, that being the atmosphere, and then you put in the outlines of the continents and the topography of the ocean, it produces an El Nino. And that, honestly, is pretty amazing. So don't knock any of these models. Just the fact that with pure physics and nothing else, you can get a model to produce an El Nino is amazing. But it's clear that some of these models are too weak, some of these models are too strong, and some of these models are just right. Goldilocks. Yeah. It isn't just about producing El Nino. What about reproducing the effects of El Nino in the places where we live? Here's another example. This is for winter rainfall in Florida, which has a strong El Nino signal. There's a very strong correlation between winter precipitation in Florida and El Nino. So the observed correlation is about 2.25, and that's between the entire index. So we're looking at neutral, La Nina, and El Nino. The observed correlation between El Nino and precipitation in the winter in Florida is 0.25. Again, what do you see? You see some models are too strong, some models are too weak, but this figure has a very, very important conclusion that you can infer by visually averaging the colored bars. And this conclusion is borne out by published study after published study. It's the conclusion that the all-model average is nearly always closer to reality than any single other model. So I have been in so many assessments and so many projects and so many studies and research groups where people are agonizing over which climate model to use. And if you have the luxury of about a 2-year funded postdoc, you can do a really good job looking at the ability of the models to reproduce the exact atmospheric circulation or ocean circulation pattern or interaction or feature that matters to your specific impact. But I've only ever had that opportunity once in my life. Most of the times you don't have that luxury. Here's the good news. If you are able to use a bunch of different models, the average is almost always closer to reality than picking your best models. And over the continental US, a number of studies have shown that this is the case. Now, over the Arctic, there's a couple of studies over the Arctic that have spent those 2 years. And they found that there's a group of models that don't get sea ice dynamics over the Arctic. So there's published papers that specifically list the climate models that don't get sea ice dynamics over the Arctic. So if you're in the Arctic, you actually have a reason to keep those models out. But over the continental US, there are some papers that make arguments one way or another. But the problem is that if you're just looking at model performance, performance and you're not looking at the model ability to capture the physics, then you're looking at how well the model does under current conditions. Does that mean the model will do just as well at predicting future change? Not necessarily. It used to be very popular to weight the models based on their ability to simulate the current conditions, but they found that when you weight the models that way, sometimes you actually end up with a worse prediction because ability to simulate the status quo does not translate into ability to simulate change. So unless, again, you have the luxury of actually studying the GCM's ability to reproduce the physical processes that matter to your impact, the best thing you can do is use one. And you'll be pretty safe because the good ones and the bad ones actually average out, which really makes any way that happens. All right, last source of uncertainty. And after I've gone through these four, we'll take a break for questions. If any questions, write them down, don't forget. The last source of uncertainty is future scenarios, and this one is big. We use a bunch of different future scenarios. These are the SRES scenarios, but the RCP scenarios cover the same range and then go a little bit lower. And the biggest issue I run into when people look at this range, and when the people looking at this range are physical scientists, is that whenever we look at a range of data, we say, oh, well, fit a normal distribution to it. The errors are usually Gaussian. That means that the most likely one is probably right in the middle. Because if you look at a physical data set, if you look at a data set of observations, if you look at a data set of anything to do with life or the physical sciences, 9 times out of 10, the errors are pretty Gaussian, unless there's a big bias in the system. And so the most likely outcome is right in the middle. And I just told you with the climate models, right? You take all the climate models, you put them together, that's physical uncertainty. The most likely outcome is in the middle of the climate models. And now, when we look at scenarios, people say, okay, well, clearly the most likely outcome is in the middle of the scenarios too. But hang on a second. What type of uncertainty is this? Is this uncertainty in the physics, the chemistry, or the biology of the climate system we're looking at? No, it isn't. Where does this uncertainty come from? Humans. Do humans act all the time in a rational, normally distributed Gaussian manner? No. If they did, we would all be out making a ton of money on the stock market, right? Humans behave in a completely skewed way, in a completely unpredictable way. Politics, economics, technology, they don't look anything like a Gaussian distribution. So we can't use this approach to determine the most likely scenario. In fact, you may say, well, the most likely scenario is either that we do something or that we do nothing. So it might be bimodal distribution is the most likely. Or you could say that the most likely is that we continue on the current pathway, which is actually heading above the red line right now. We can continue on our current pathway until something bad enough happens that we have this collective oh shit moment, and then we go as quickly as we can down to the lower pathway, and we end up following a scenario that's not even on this graph. I mean, if I had to put money on it, that's the one I would put money on. So the IPCC knew this, and so in the fine print where nobody ever reads it, they very explicitly said you cannot assign a likelihood to any of these scenarios because you can't predict human behavior. In fact, you know, there's a chance it could be above or below because you never know what's going to happen. So what do I do when I try to develop projections for, say, the city of Austin's water supply? Or the health department for Washington, D.C. is worried about the impact of heat waves on health. What I try to do is I pick a lower scenario and a higher scenario. This is an example of what that looks like. And I pick a range of climate models that give me the uncertainty. So this is the human uncertainty, a lower and a higher scenario. This is the global temperature change here. And this is the scientific or model uncertainty to cover a reasonable range. And I'm very careful and clear with them to say, you know what? The difference between these scenarios is not a scientific uncertainty. The difference is up to us. In fact, here's the cool thing. Here's where quantum mechanics comes into it. If you ever took a class in quantum mechanics, or you ever even watched a TV show about it, they probably brought up Schrodinger's cat, right? It's the idea that the act of observing the cat in the box can determine whether that cat is dead or alive, which totally makes you not want to observe the cat. In the same way, putting a positive spin on it, in the same way, I think that the likelihood of the higher scenario would be virtually 100%. if there were no climate scientists doing impact assessments? Let me put it to you this way. If you didn't know that smoking caused cancer, if we were told that smoking relaxed us, calmed us, made us less anxious, how many people in this room would be smokers? Put your hands up and be honest here. Yes, why not? It's harmless. It makes you feel calmer, it makes you feel relaxed, something you do in social situations. But the reality is today, most of us don't smoke, and those of us who do smoke know that we do so with health consequences. Why? Because physicians did the research and showed us the consequence of our actions. In the same way, how many people eat cake and donuts for breakfast every day? I wouldn't mind doing that. But I don't do that because I know what that does for my health. In the same way, if we didn't know what burning fossil fuels would do to our planet, I think there's virtually 100% chance we'd be on a higher scenario because we wouldn't know what the consequences were. So what I tell people when I work with cities, when I work with federal and state agencies, when I work with nonprofit groups, is I tell them, first of all, the choice between the scenarios is not a scientific choice, it's a human choice. And second of all, the act of doing this assessment, of quantifying the risks for Washington, D.C., for Chicago, for Austin, for the state of California or Delaware, the act of quantifying these risks is actually changing this probability as we speak. Because you're creating a city or a group or an organization or even a state full of people who are now conscious of the difference between the higher and the lower scenario for their water supply, for their wine grape industry, for their heat wave risk and their health, for their asthma probabilities. So isn't that cool? By doing the science, we're actually changing the probability of these scenarios. That's why we can't assign probability to them. And that's why I do so many of them, is because I'm trying as hard as I can to change the probability to get us down to that lower pathway. So the last and most thing to mention before we end the section on certainty is there's these great papers by Ed Hawkins and Rowan Sutton that show us how the proportion of uncertainty changes over time. The further out we go into the future, the less important natural variability is, and the more important human uncertainty becomes. Now that's for temperature. For precipitation, scientific uncertainty stays very large. Although for certain regions like northern latitudes, it becomes smaller because we see very large change up in northern latitudes. Why do you think scientific uncertainty stays so large for precipitation? Gets back to scale, exactly. So that's why a lot of the cutting edge research in climate modeling relates to precipitation and convection. So this is all about what we don't know, but here's the one thing that we do know. This is what we know. If we don't factor climate change into our long-term planning, we're going to get the wrong answer. In other words, if we just continue on the status quo, even though the future has a large uncertainty range associated with it, if we continue on the status quo, even the bottom edge of that uncertainty range will be above where we were in the past. That's why we need future climate changes. All right, questions, comments, clarifications? Okay, sure.
So in the earlier comment about how scientists are underestimating climate change, did it give did it give a number, like a degree of underestimation, or?
It didn't, because they were looking at all kinds of things. They were looking at the rate of melting of the Greenland ice sheet, of the Antarctic, sea level rise, change in ocean circulation, plants and animals and insects moving north. So it wasn't just temperature change. So they couldn't, because it was so many things.
Yeah. All right, thank you.
Yes.
So I know you talked about how it's better to use many climate models so that you can get that average. Can you clarify? I mean, I sort of know the difference between statistical and variability.
We're going there next.
Oh, awesome.
Yes. We're talking about downscaling next. We're just talking about climate models.
Okay,
Yes.
cool.
My question would be about the human uncertainty. Is there any studies that sort of trying to predict based on the economic development and where we all, because some economies grow up and based on GDP we can assume that emissions grow, some economies go down. Is there any predictions based on that?
Well, these scenarios are actually based on exactly those predictions. Each scenario here has GDP, population, demographics, technological development, degrees of the extent to which people become more interdependent versus more dependent, interdependent versus independent, yeah. They have different storylines associated with them. So that is what goes into this, but economists know that they can't predict GDP. They can't predict it, but they can say, you know, if X, Y, and Z happen, then here's where we go. So they develop these stories of the future, and each of these lines is actually a story. Yeah. So there's a ton of detail in there, which you don't see from just looking at this thing of carbon emissions. But unfortunately, it's not predictive because in economics, they definitely have economic models, and they can use them, you know, to develop, associate with each of these emissions. They have all the economic data associated with them, including population and 1 by 1 degree grid cells all over the world and things like that. But they're all different pictures of the future because they don't respond to external forcing like the climate system does. Like the climate system responds to carbon dioxide, responds to volcanic emissions, it responds to changes in energy from the sun. But the economy responds to crazy stuff that we can't predict. Like the fall of the Soviet Union, for example. Economists did not see that one coming even a year ahead of time. And it completely altered the world's economy. So, yeah.
Did it help their emissions?
Yeah, it did. Well, actually, what happened was it gave Russia what they call a lot of hot air. Because in the Kyoto Agreement, which is back in 1996, nations had to reduce their emissions below a historical baseline. Well, it turned out Russia reduced its emissions radically simply because the economy tanked. So Russia had all these hot air credits that it then sold to all these other countries and made a ton of money on. Because it didn't actually have to reduce its emissions because it absolutely did so anyways. So that was actually a problem.
The reason I'm asking about GDP is that what I know from my classes in Ukraine, the carbon dioxide emissions and the Ukrainian GDP is just the same graph over the 20 years.
Right. Yes. Okay. So this is really interesting, and I'm going to see if I can Google or find this because just this year, so up until the 2010, GDP and carbon emissions were like this. One went up, the other went up in step. Thanks to enormous technological advances in China and the United States and in the European Union, GDP and carbon have started to uncouple. And we're actually seeing the data, because economic data takes a couple of years to come out. So we're only seeing the data now from about 2 years ago. So I'm going to try to see if I can find that. So carbon, GDP. I just read a couple of articles about that in the last few months. So it's really interesting. Okay, here it is. Here it's March 16, 2016. So this is just 3 months ago. This is from the IEA, which is the International Energy Agency. This is pretty cool. Decoupling of global emissions and economic growth is finally confirmed. For the second year in a row, carbon emissions stalled while GDP continued to climb. Yeah.
So rather than that.
Yes, we're heading there.
Okay, I have
It's not
the
fast.
last question on this matter. So what is the story behind the tallest increase in emissions?
The tallest increase in emissions is based on continued dependence on fossil fuels with substantial technological innovation. If we look at the last decade or so of emissions, and let me see if I have this here. I think I have a figure where I can find it. Let's see. Let's see if I can find a figure. So I actually made a figure where I had the scenarios and real carbon emissions on it. And let's see if I can find it here. Yes. Okay. So here are historical carbon emissions. They were growing about 1% through the 1990s. And then through the 2000s, they were growing about 3% because of developing countries like India and China. And if you put the emissions on it, the blue are the new RCP scenarios and the red are the SRS scenarios. You see that we are at the higher end. So things were not looking good, but things are starting to turn around now because of the huge advances in solar and wind technology. I mean, we've gotten to the point now, this is crazy, where China has more wind and solar installed than all the rest of the countries in the world put together, which is pretty cool. And so we're seeing these changes happen, but the issue is they're not happening fast enough to hit the lower scales. if we were at this point in 1980, so if we had 1980 carbon dioxide levels and we had 2016 technology and renewable energy prices, I think we'd be okay. The problem is that we've spent 35 years not doing much, and that's really the problem. So it's an acceleration that we need now. It's starting to happen, which is very cool. Other questions? Yes.
You talked about the average, sort of all of the models being generally better than any individual model, and not something I ever understand. But I often see people looking at them and sort of temperature pieces and saying, well, look at one
Yes.
So what, does it just depend on the questions it is asking you, or are there some real pluses and minuses of how you can solve them,
So that kind of hot, dry, cool, wet approach is one that has been quite popular over the last 15 years or so, especially when your resources are limited. You can only pick like 2 climate models. So California took that approach for a long time. So I actually just ran into that working with the city of Austin. Somebody brought that question up because they said, well, all the water utilities we know in California all take this kind of quadrangle approach where we use 2 climate models and we use them to kind of down the thing. So I said, well, here's the problem with that approach in Texas. In Texas, we don't expect a change in average annual precipitation. There is a pretty overwhelming consensus that there's no change in average annual precipitation. Now, there is definitely a change in the variability. So we're going to see stronger, longer droughts, and we're going to see more heavy precipitation. But we're not going to see much change. So picking models based on one is wetter and one is drier just doesn't make sense. So it really depends on where we're at, and that's why the National Climate Assessment is such a useful resource. So Chapter 2 of the National Climate Assessment, and there's actually a new National Climate Assessment climate report coming out. It will be out, I think, actually, it won't be out for another year, but we just finished the first draft. So for now, use the National Climate Assessment, NCA3, and there's a chapter for every region. The chapter for our region, the Great Plains, was written by Renee and other people. The Chapter 2, Our Changing Climate, which was the one I worked on, has a lot of really good maps. I'm going to show you one of these maps that I think is really outstanding. It is, where are you? Here we go. These maps, right here. These guys. Okay, so what do we have here? We have the higher scenario on the right and the lower scenario on the left. So there's a higher and a lower scenario. And then we have change in precipitation by season. And where you see the hatched lines, I don't know if you can see those hatched lines, that's where the models agree. So this is really helpful because it shows you for your region what type of seasonal pattern you'd expect. And what you can see, what really stands out to me is when you compare the higher and the lower scenario, it's the same pattern, just gets stronger in most places. So this helps you see for your region and for your impact how you might want to pick your future projections. Because if you only really care about summer, if you're studying something where summer only matters, well then you look at summer and you'd be like, okay, well, if I'm in the Oklahoma, Central Great Plains area, Oklahoma, Nebraska, Kansas, it looks like it's getting drier, and there's model agreement that it's getting drier, right? I mean, that's crosshatched. So it doesn't make sense for me to pick a super wet model just to pick a super wet model because the models pretty much agree it's getting drier. Now, if I pick a bunch of different models, that's nice because it'll cover the range. If you have the luxury of picking 8, 10, 12 models, then you'll get a nice range. You'll get a center, you get a distribution, a standard deviation. If you can do that, it's really a good thing to do. But if you can't, then again, what type of uncertainty is this that we're looking at here? It's not human uncertainty, it's physical uncertainty, which means that you can assume a normal distribution and you can assume the standard deviation in the middle of the distribution most likely. So the answer to that question is very nuanced depending on what type of impact you're looking at where you are. Because in some cases the answer would be yes, you do want to do that. Like, what if you live in an area where there isn't agreement? Where the models don't agree, where they average out to no change, but some show wetter and some show drier, then you would want to take that approach. But if you live in an area where there is model agreement, then okay. Any last questions before we talk about downscaling? Derek, you've been saving your question till the very end.
Okay. So a lot of the recent research, especially with Claire Besser's group of
Yes.
NCAR, is looking at that maybe the natural variability and uncertainty is
That's right.
greater than we thought. I was talking to people here, so much so that in central Great Plains, with the next 50 years, the trends in precipitation, temperature with no other changes, but the same model, same portion, 40% increase in precipitation, 40% decrease in precipitation, reasonably locally. So how do we communicate that uncertainty to stakeholders on the ground?
Yes, that is a great question. And I think it's not as hard as we might think, because stakeholders on the ground, if they're informed stakeholders, so if they're water planners or engineers, they're familiar with patterns of natural variability in the past. And so when we run stuff out into the future, framing stuff in terms of, I always frame it in terms of 3 categories. A risk that we don't know how it's changing, but we know it won't go away. And a classic example of that is tornadoes. Do we know how climate change is going to affect tornadoes at the local scale? No. Hopefully. We do know. I don't think we do. But we do know they're not going away. If you live in Oklahoma, I would be shocked if you didn't have tornadoes there in 50 years, right? So that's category 1. We can prepare for risks we already face today that are not going away. Category 2, we can prepare for risks that we know might be changing, but we don't know the exact numbers on. So for example, in the central Great Plains, even if our actual precipitation doesn't change, as temperature increases, our evaporation rates increase and our drought risk does increase. And so we have a paper, for example, looking at drought risk, that even when you incorporate natural variability with a large range of models, we do get greater drought risk with no change in annual precipitation. Can you put numbers on it? It's tough because of those, the year-to-year and decade-to-decade variability. And then category 3 are the impacts that you can put numbers on, and those are typically temperature-related, specifically looking at, say, the frequency or duration of heat waves or extreme heat events or days below or above freezing or things like that. And so often when you couch it in those terms and you tell people this is what we don't know, but this is what we do know, and this is what you already know, it's almost like a relief for them. Because they're used to coping with historical variability. They understand that. And when you kind of give them the green light to say, yeah, if this is what you're concerned about, then yes, historical variability gives us 90% of the information we need to move into the future. We just add this little extra bit and you're good. So I don't think it's as big a problem as we often think. Often, for us as climate scientists, we're the ones who want the deterministic answer, and it kind of blows our minds when the range is too big. But people on the ground, like a water manager, they're used to dealing with massive uncertainty all the time. And when you tell them, look, you already have massive uncertainty, and that massive uncertainty is going to be there in 50 years, they're like, oh, okay, I get it. So I've actually never had a practitioner freak out over uncertainty before. They freak out when they think, like when we kind of walk through, these kind of things, and we've shown that it can be quantified. I've never really had anybody freak out about that before. They freak out more over very deterministic narrow solutions because it's scary because they know that's not the way the real world works. And so often with climate projections, especially when we use them naively, we tend to say for example, here, people might, we might take all of these number of different models. How many models are there here? 3, 6, 9 models. We might average them together and then average over time and then give a city one number. So a city might get one number. And then, just a second. And then instinctively, the city planners, that one number freaks them out. Like, how can you give me one number of what our average temperature will be like in 2070? So that is honestly what freaks them out more, is certainty.
I like that.
Okay, what were you going to say? Yeah.
In terms of human psychology and Gauss, that whole enlightenment of mathematics kind of was funneled into psychology a little bit. Most of what educational psychologists do and most of what psychologists do in interpreting quantitative survey research is trying to fit and say that the brain is normal and that it's not normal.
Right.
And so how do we get out of it?
Oh gosh, so my husband does social science research. He studies how people learn language. He actually does experiments with people who try to figure out how the brain learns a language. And it is so hard to generalize populations. There are a couple of things that you can tease out that do work across broad populations, but there's so many ways in which we differ. And that affects the way we interact with the world. You know, honestly, I think my lucky stars almost every week I'm not in social sciences because I feel like it's way harder than physical sciences trying to figure out how the brain works. I don't know if that's an answer. I don't think it is.
There's no right answer. I mean, it's hard to convince people that it's non-linear because that to them is uncertainty, and that is not good. You can't publish that.
Yes. Well, I mean, but you should be able to publish it. I mean, if you even in the physical sciences, if you get a no result, you should be able to publish it because no result you learn something from. But I mean, even like look at the polls. I don't know if you guys were watching TV, but I will never forget this. I was watching TV during the last election when Fox had been running polls that said that Romney was going to beat Obama. And my husband loves watching politics, so he was flipping through all the channels, and we were on Fox when Karl Rove freaked out and said that Obama could not have won, and literally ran downstairs and had a cameraman follow him into the room with the pollsters in the room, guys counting the numbers, to basically grab them and say, this can't be true because the polls said it wouldn't happen. That was a classic example. Polls are what? People's opinion. People's opinion change. Sampling rates are different. People change between when they're driving to the poll, who they vote for. People might not have come to the poll or might have come to the poll. And that was just a classic example of how difficult social science is. I mean, honestly, I feel like I should have a little video of that. Show what I mean. I've never seen anybody do that before. I've never seen a person at a desk, you know, doing commentary actually leap out of their seat and run down the hall, dragging a camera with them. Yeah, and going down, and like the guys at the computers, you could see when he came in the room, they're like, So, and then I met somebody that, shoot, who did I just meet? I just met somebody like last week who knew one of the guys who had to actually say to him on live TV, no, this is correct. I was like, oh my goodness, what a terrible introduction to live TV. So, all right. Unless there's any more burning questions, let's move on to downscaling because we have to move through downscaling very quickly. I have a little boy in basketball camp that has to be picked up, unfortunately, which means I have to be out here in 15 minutes. So this is going to be the fastest downscaling talk you've ever heard. Pay attention. Try to be Canadian. All right.
Downscale?
Yes, I'm downscaling my talk. How do we get from these big scenarios through the global models to the level of the individual city? We do so by downscaling, and downscaling is not regridding. I know I said that slowly and I wasted a few seconds, but I'm going to say it again. Regridding is not downscaling. You are adding precision, but you are adding no more accuracy. Downscaling in the context of climate information adds new information. It can add new information in one of two ways. It can add it from observations, in which case it is empirical statistical downscaling, or it can add it from regional climate modeling by having higher resolution modeling of the physical processes. That is downscaling, adding new information. It is not just regridding. Regional climate modeling. Regional climate models are basically a combination of climate models and weather models. In fact, WRF is used for regional climate modeling and weather modeling. They are rectangular models that can have higher resolution, anywhere from 1 kilometer, sometimes even urban models have 1 meter, which is crazy. But, you know, over large areas, anywhere from 1 kilometer to about 50 kilometers. And compared to a global model, they're very similar, but they have some differences. Because they have rectangular boundaries, they need boundary conditions, which they get from the climate model. They get their natural variability from the global climate model. They don't create it themselves. If there's an El Nino, the El Nino comes from the global climate model into the regional model through its boundaries. Think of it as this grid, and at the edges, it's getting the weather system coming in and going out the other side. It's getting the ocean current coming in and going out the other side. But it has much better resolution. Let me give you an example. This is observed average summer temperatures over the continental US in 1990s. This is a global model simulation, for example. And then here's what it looks like by the time you put it through a regional climate model. It looks dang good, doesn't it? Note of caution. Regional climate models are physical models and they can completely disagree. This is some pictures I got from NARCAP, and I'm going to admit I picked the worst ones. I actually went through the NARCAP website that has a lot of regional climate models, and I went looking for the worst ones. So this is the worst you can find, where this is a month worth of, or a season worth of precipitation from the SC-CSC global climate model on the left, and on the right you have 3 regional climate models downscaling that same information. Isn't that interesting? Pretty different. So that is why, because these are physical uncertainties, that is why it makes sense to use several of them if you can too. This was a study they did in Germany, where they looked at how a regional climate model could reproduce windstorm damage, for example. How correlated were they with observed windstorm damage? And they found that the x-axis there is number of regional models. The more regional models they used, the more likely it was that their average would be correlated with the real world. Now, I know this is challenging because we don't often use multiple regional models. We usually just use one. But the good news here is it showed even using 2 made a big difference. And again, the more of these you use, the closer and closer you kind of converge on reality. Why do we use regional climate models? Because they give us a lot of good information. What if you wanted to study the viability of a solar panel array in Africa? You can get cloudiness and solar energy from a regional climate model. What if you wanted to study if we should install a new wind farm in South Texas? You can get wind patterns from a regional climate model. What if you wanted to study the impact on agriculture? You can actually couple a crop model with a land surface model with a regional climate model. They can do amazing things. But they have some drawbacks too. Compared to statistical models, number one, they can generate a lot more variables, even ones that weren't observed. So if I'm doing climate projections for the middle of Africa, I have a choice. I can use one weather station or I can use a regional climate model. I can bet you I would be using a regional climate model. They can be used in places where observations don't even exist. But they're computationally intensive and they still have to be bias corrected if you want to use the absolute values that come out the other end. Statistical models are limited in that they can only generate variables that have been observed already in places where those observations exist, but they're very affordable computationally and they do incorporate bias correction right into them so you can use the output directly. If it says 95 degrees, it is 95 degrees. You don't have to correct for the biases. So what is statistical downscaling? Statistical downscaling essentially assumes that our weather here today in Lubbock is a function of 3 things. It's a function of the large-scale weather system covering this part of the country. It's a function of our local orography and topography, where we're located relative to the Gulf of Mexico, how flat or how mountainous it is, all that kind of stuff. And number 3, stochastic noise. What are we trying to do? We're trying to take, typically, a distribution, which can look a little bit squiggly and messy because it's based on a limited sample of observations, and we're trying to, in some intelligent way, fit to that distribution. That's basically, in a nutshell, what a statistical model does. Now, you don't want to overfit, because if you overfit, you're accounting for errors in the observations, possibly. Or you're accounting for events that aren't actually that common because we're undersampling, we don't have long enough data. So when you're doing statistical modeling, we have our uncertainties in internal variability, the science, the scenarios, but then we're also making 3 other big assumptions. We're assuming, number 1, that our observations don't contain errors. Anyone who's ever worked with observations at this point is welcome to give a hollow laugh. Because they do. They contain horrible errors. In fact, we have found new errors in the GHCM database, which is one of the most quality controlled and constantly checked databases, I think, in the United States. We have found errors in that database through using it to do our downscale. Errors that included days that were like minus 38 degrees Celsius in a location in Florida right next to Miami, which really screwed up our downscaling. We had to find out why. It turned out it was the observations that were screwing up the downscaling. You have to also make sure that the predictors you're using are relevant to local climate. Because, for example, there's a really good correlation between winter temperature in Northern Europe and sea surface pressure over the North Atlantic. But as climate changes, that sea surface pressure dipole isn't expected to change much. So if you use something that had a good correlation historically as a predictor, you'd say, oh, well, it's not supposed to get warm at all. What are you talking about? You have to make sure you're using the appropriate predictor. And then the last uncertainty is possibly the most tricky one. That is the uncertainty of stationarity. What do I mean by that? I mean that we are developing this relationship back here, right? We're developing it based on what? Based on historical data. Is this relationship going to hold true in the future? I don't know. We don't have data in the future, right? Well, we don't have data in the future, but thanks to Keith, we do have 25-kilometer high-resolution global simulations in the future. So what we've done is we've taken those 25-kilometer high-resolution global simulations as observations for the end of the century under a higher scenario. And we train and evaluate our statistical downscaling models on a much coarser grid typical of a GCM, 250 kilometers. And then we take our downscaled temperature and precipitation, and we take our future observations, and we compare them to see what the difference is. You want to see? Pretty cool. So,
What's time variant?
time invariant?
Yeah.
Oh, doesn't change over time. Sorry. That's one of those words. So here we've got 3 different downscaling approaches. Unfortunately, these are in the wrong order because the simplest one is in the middle. It's in the delta approach that we use in the World Cup database. Then we have empirical quantile mapping, which is used in the SC-CSC database. And then we have a parametric quantile mapping, which is used in the USGS database. So this is very simple, this is medium, and this is more complex. I should have rewritten the order by the slides. So this is looking at the bias at the top in the 1/1000th coldest day of the year. That's pretty extreme, isn't it? The middle is looking at the bias in the median of temperature, and then the bottom is looking at the bias in the 1/1000th hottest day. And so basically, that's the hottest day in almost 3 years. So what do we see here? We see some big biases up at the poles, right? But things look pretty good in the middle. Which means what? It means that our assumption is not stationary under those statistical methods for extreme cold or hot temperatures at high latitudes. But it is stationary for average conditions pretty much around the world, although you still do have some problems with high latitudes. Now here's precipitation. This is really interesting. These are the same 3 methods. This is the 10% wettest days, 50% wettest days, and 90% wettest days. The method on the far right is the method that was developed for and is used by people who do water modeling. And it is amazing. I still remember when I showed them this figure for the first time, they were like, whoa, we had no idea. It's like, you have somehow serendipitously developed the perfect method to do streamflow forecasting because they don't care about precipitation over any time scale shorter than 2 weeks. So the 90th percentile of the distribution is about as fine as they go with hydrological modeling. This method, empirical quantile mapping, is absolutely perfect for that. But what happens if you go to extreme wet conditions? What happens if you go to the 99th or the 99.9th percentile of the distribution? Oh my goodness. Incredibly high wet biases. So you don't ever want to be using that method to look at extreme precipitation because you would get totally wrong answer. So this is pretty cool. So bottom line, if you look at, say, days per year over 95 degrees, this is, I think, for Atlanta, that's the red line, or the orange line, and you look at growing degree days, which is accumulated over a long period of time. And here in this figure, I used 5 different downscaling methods from simple to complex. You get the same answer from all of these methods when you look at a seasonal average. They all give you the same answer. They give you a different answer for the extremes. Why? Because simple methods don't resolve the tails of the distribution. So what you're looking at here, the differences here are not scientific uncertainty. You shouldn't say, oh, well, if I'm doing temperature extremes, I should use a lot of different methods. No, what you're looking at is the fact that simple methods aren't ever meant to do extremes, because they're not built to do that. All right, bottom line on downscaling. We're doing good. We have 1 more minute for 2 conclusion slides. Just about any downscaling method is better than using climate model output directly because climate models have biases that need to be removed before you can use the absolute values. It's not their fault, it's a matter of scale. If we had millimeter scale climate models, they wouldn't have these biases. Simple methods are surprisingly good if you're looking at winter, summer, spring, fall. But if we're looking at the tails of the distribution, we need more complex methods that do resolve the extremes. It's important to understand the limitations and the biases in the methods in order to pick which one you want to use. So then you might say, okay, well, how do I know which one to pick? I'm going to leave you with 3 resources. Ready? As part of the Infrastructure Climate Network, it's an NSF-funded center, we've done a ton of webinars. So if you go to theicnet.org, don't go to icnet.org because that is a Danish knitting website. And here's the total irony of it. Ann Stoner, who some of you know, has an awesome NSF postdoc funded through the center. She is Danish and she knits. So I think that's just awesome. Anyways, theicnet.org. If you go to their outreach page, they have webinars. They have webinars from regional climate modelers. They have webinars from me. They have webinars from a lot of people who do observational stuff. Check out their webinars. Fantastic resource. Number 1. Resource number 2. If you actually want to get your hands dirty and look at some of the stuff we've done, the USGS website has it. You can download them by watershed, by grid, by ecoregion. It's really cool what they've done with this mapping tool. I love it. Give you a minute to write that down. Or you can just Google USGS downscaled. It'll pop right up. And then this just came out 2 months ago. This is a report that was commissioned by the Department of Defense, their Certainty program, and it's a report and a webinar. The report is called Use of Climate Information for Decision Making in Advanced Research State of Art Understanding. If you want to find it, I didn't give you a website because they didn't give you a nice website. Just Google Certainty Downscaling or Certainty Climate. It'll pop right up. There's a nice webinar that goes through the report, and then there's the report, and I really do recommend it. It has a lot of the nuances and a lot of the details in it, and it's specifically aimed at, if I want climate projections, how do I pick them? That was the whole point of the report. So those are the resources I'm going to leave with you. The ICNet webinars, the database where you can fool around with the data yourself, and most of all the Certainty webinar report because it's brand new and it really crosses all the T's and dots all the I's. And that's it. Thank you.